everyone. I'm so glad to see so many faces in the room. Thank you all for coming. I'm really delighted to introduce our students, but maybe let me tell you a little bit about the project first. So our RTG grant, this is an NSF grant for Commutative Algebra at Nebraska. It covers the cost of an REU, that's a research experience for undergraduates, each summer for 4 students. So every summer we do this project with 4 incoming freshmen here at UNL. So you're about to meet 4 of our incoming freshmen. And each summer they are mentored by 2 of our amazing graduate students. So this summer, Sara Mueller and Isaiah Martinez, they were the mentors of our wonderful 4 students. So you're about to meet, maybe not in order, Faisal and Chris and Taw Dee and Steven. And they're going to tell you about the project that they did this summer. Now, they'll tell you something about graphs, which is really fun. Let me maybe just preface the work they'll tell you about by saying that secretly what they're doing is motivated by a problem in commutative algebra. But this problem has been translated to a problem about graphs, which is what you're going to hear about. Great. Thank you.
All right. Hello, everybody. Welcome to our presentation about graphs and their relation to D edge density. My name is Chris.
My name is Faisal.
My name is Taw Dee.
I'm Steven.
And before we get too deep into this topic, we have some important definitions to go over, and then we'll be able to share some results with everybody. So a part of our summer has been focused on the topic, like Eloísa said, in graph theory. And instead of the usual X and Y graphs everybody knows, we've been dealing with a combinatorial object consisting of edges and vertices. And figure 1 shows an example of a graph that we've been dealing with. So as you can see, the solid lines here indicate an edge, and the solid black dots indicate vertices.
Oh, it's my fault. It's my fault. I'm so sorry. Now it's going to work.
Okay. So as we can see here, we have a complete graph K4, indicating that it has 4 vertices. And these are just some subgraphs of K4 with 3 edges, as we can see here in figure 3. And a subgraph is basically just contains a subset of edges and vertices of the original graph.
And so moving on to important definitions. One of our more technical terms is edge blankets. What are they? The rigorous definition is this. You let G be a graph of the vertex set and an edge set. A subset of edges defined by J is an edge blanket if for all edges or for any particular edge in that edge set, the vertex set of that particular edge intersects with the vertex set of your subgraph. So what this basically means is that when you take a regular graph and you create a subgraph from it, it is an edge blanket if it is able to touch every single edge in that original graph. And so how it looks like is this, indicated by the green edges here. This would be a sub-blanket or an edge blanket because all the edges in our subgraph are able to touch all 4 of our edges in our shape right here. But a counterexample would be down here with the red edges indicated. As you can see, only 3 edges in our original graph are being touched by our subgraph, leaving this single edge untouched, leaving this as not an edge blanket.
So another important definition that we have to know for this presentation is internal edges. This is the rigorous definition. Let G be a graph with a set of vertices and a set of edges. A subset of edges J has an internal edge if there exists an edge in J that is internal. And so this is what I'm talking about. This top graph up here represents a graph that has a subgraph represented by these green lines that has an internal edge. An internal edge is basically an edge. If you were to remove this edge, all the vertices in that subgraph will still be touched by other edges. So if you were to remove this middle edge right here, these 2 edges on the outside will still be touching all of the vertices in that subgraph. However, this This down here is an example of a subgraph that doesn't have any internal edges. Because if you were to remove any of these edges, there would be at least one vertex that's not being touched. I should also note that these are examples, this and this, they're examples of edge blankets as
well. So our main objective is to determine a graph's edge density, and this is a value. So above here is our definition. So in other words, we want the value of B for which every possible selection of B amount of edges satisfies at least one of two criteria. And that is that the selected edges either form an edge blanket or that they concern an internal edge, both previously mentioned. So in this example, the graph C5 shows how we apply the definition. When we select three edges, these are the two possible subgraphs with three edges in the green. So the green satisfies the required criteria of having an edge blanket and or an internal edge. So for example, this example on the right, it's an example of an edge blanket because the edges in the green could touch these remaining two edges in the original graph. And this example on the left is both an example of an internal edge and an edge blanket. It's an example of an internal edge because let's say if we remove this middle green edge, then the vertices in the original, the vertices in the green subgraph would still be touched by these other two green edges on the outside. However, in figure 7 down below, the red shows selections of only one or two edges. And since these two subgraphs are counterexamples that don't contain an edge blanket or internal edge, we can conclude that C5 is not one or two edge dense. Thus, its minimum edge density value will be 3. Now, before we continue on, does anyone have any questions about edge blankets, internal edges, or the edge density? No? Perfect.
So our first proposition is, if G is a graph with n many edges, then G is n edge dense. Now question, if we have a graph of G with n many edges, what subgraph can be formed from that? Anybody? Well, the subgraph will just be itself. So as we can see here in figure 8, we have an example of a graph with 8 edges, which includes all of the original edges. And because of that, it forms a silly edge blanket all around, making this 8 edge dense.
Okay, so for our second proposition, it states if G is D edge dense, then G must also be D plus 1 edge dense. And as we stated earlier, a graph is considered D edge dense when all of its subgraphs containing D many edges are either edge blankets or have internal edges. And so this means that adding edges to possible subgraphs that already have internal edges or edge blankets is unnecessary because you just be adding more, you just be covering more space. So for example, this graph on the left has a subgraph that has 2 green edges. And then it's 2 edge dense because when these 2 edges touch every other edge in the graph. And you can see that by adding one more edge onto this subgraph, it doesn't take away the fact that there was already an edge blanket, and so it is also 3 edge dense. And this proposition is why we care a lot about the minimum edge density of graphs. Once we know the minimal edge density, we know that a graph is edge dense for all edge densities above that edge density.
Before we move on to our next proposition, we'd like to introduce some criteria. Throughout our research, we've been dealing with a question, and that question is, what is the smallest edge density that a graph can have? And so to prove that D is the minimum edge density value, we need to show 2 things. First is that D minus 1 doesn't work by finding a counterexample, which is a subgraph with D minus 1 edges that doesn't have an edge blanket or internal edge. And second is that D does work for every possible choice of edges through induction. So Now we'll propose star graphs. So you defined a star graph as having one center vertex and every edge connecting out to it. So I'll draw an example. So one center vertex, and we can draw edges out from it, give them vertices. So we could label this graph S4. So because of that, any single edge would touch every other edge through its center vertex. So this center vertex pretty much acts as like a hub. It can come out to every other one. So it forms an edge blanket by definition. Therefore, we can say that every star graph has a minimum edge density of 1. So again, in this example, the green edge represents any chosen edge for n amount of edges. So since every edge shares the same center vertex, one edge would always form an edge blanket. And again, the minimum edge density would be 1.
Okay. We're transitioning into our theorem. Our theorem has to do with this type of graph called a flower. And a flower graph is basically where all the petals in the graph share a vertex in the center of the graph. So right here. The petal consists of 3 edges and 3 vertices, including the shared vertex. 2 edges of the petal are connected to the center vertex, while the third is connected between the 2 non-center vertices. This is an example of a 3-petal flower, which we denote as F3. So our theorem is the minimum edge density of every flower graph, Fk, is 2k minus 1, where k is the number of petals. And thus this means that all flowers have an odd minimum edge density. Okay, to begin our proof, we'll show that a flower's edge density cannot be 2k minus 2. And in this figure, it shows counterexamples as the number of petals go up. And these subgraphs, indicated by the red lines, were selected to not have any internal edges. This is so that we can find the minimal edge density. And you might also notice that these resemble star graphs. And as you can see, these subgraphs have an even number of edges, but they're not d-edge dense because there's an edge indicated by this dotted line that is not being touched by this subgraph. So, for example, if we look at F3 right here, it can't be 4 edge dense because this edge is not being touched. However, if you were to add an edge anywhere, it will make an edge blanket or an internal edge, which will make it 5 edge dense.
So to prove this, we'll start with the base case. So let's take a look at f of 1. And f of 1 is simply a flower graph with 1 petal. And we need to find its edge density. So if you draw a subgraph with 1 edge, this is its only possible subgraph. And as you can see, this is an edge blanket because this selected edge could touch either of these edges. So f of 1 is 1 edge dense. So the base case holds. Okay, so we use induction by assuming that the flower graph f of k has a minimum edge density value 2k minus 1. Then we show that adding 1 petal gives f of k plus 1, the next petal over, a minimum edge density of 2k plus 1. And so basically, when we add 1 petal, we add only 3 new edges. So in any 2k plus 1 edge subgraph of f of k plus 1, built from f of k, at least 2k minus 2 edges must come from the original f of k graph. Since the edge density value increases by 2, those extra edges can be placed in 4 ways. First is that 0 edges are on the, 3 edges are on the new petal. We can take a look at this petal right here, from here, here, here. And those are 3 edges in a row, which would form an internal edge, so we don't really have to worry. The next case is that 2 edges could be in this new petal, so here and here, for example. The next is that 1 edge is in the new petal, and the other one would exist inside of FK. And the last case is that we have no new edges in this new petal and that they exist inside of FK. And by checking these 4 cases, we've covered every possibility.
So for the first case, we just want to show that a subgraph inside of F of K will either be an edge blanket or contain an internal edge. Now recall earlier that we are assuming that F of K has an edge density of 2K minus 1 already. What that means is that our subgraph is either already an edge blanket or contains an internal edge. And so if our subgraph already contains an internal edge, then for case 1, placing these edges anywhere does not really matter, because that doesn't change the fact that this subgraph will still have an internal edge. What we do care about the fact is that if our subgraph for F of K is an edge blanket, because upon placing our 2 new edges in this petal right here, we therefore complete our edge blanket, because it's just touching this last edge. And this holds true for case number 2 as well, because even with just one edge right here, if you ignore this bottom one, we are still touching the last 2 ones in our petal, meaning that we just proved our first 2 cases already.
So moving on to our third case. For the third case, we're proving that putting 2K plus 1 many edges in FK will create an internal edge. And it's not possible to make an edge blanket in FK plus 1 because an edge on the newly added petal is not being touched by any other edges. Okay. So if FK subgraph has no internal edges, this means that each petal should have a maximum edge count of 2, specifically the 2 touching the center vertex. And since we're avoiding 3 edges for each petal, the max edge count for the whole subgraph should be 2K. So 2 times the number of petals. And so when we place 2K plus 1 edges in FK subgraph, by counting argument, 1 petal has to have 3 edges, creating an internal edge. And here's an example of that, using a petal being added onto F3. So as you see, adding 2 edges onto F3 will create an internal edge. And this doesn't have to be exactly these 2 spots right here. It could be here or here, but adding 2 anywhere will create at least 1 internal edge. And this concludes our proof.
So moving on from flower graphs, our goal was to still just try to find as many minimum edge densities as we can for as many different graphs. And a graph that we have been looking at are cycle graphs. So if you let G be a single component graph with a vertex set and an edge set, then G is a cycle graph if for every vertex in this vertex set has a degree of 2. So think of your triangle. At a vertex, you get a square. At a vertex, you get a pentagon, and so on. So we investigated the minimal D for which the cycle graph on n many vertices was D edge dense for small n, and obtained the following data in this table right here. And so what this table is basically showing is that no matter how many vertices you have, let's say we start at 3, whenever you increase the vertice count by 3, your edge density increases by 2. So if we look back at 3 vertices, it has an edge density of 1. We add 3, go to 6, edge density of 3. Add 3, 9, 5, and so on. Other than that, we also saw an interesting pattern here in which we have an edge density that duplicates. As we can see here at 5 and 6, they both have 3. 8 and 9, they both have 5. 11 and 12, they both have 7. And so our observations led us to this conjecture where if C of n is the cycle graph on n many vertices, then the minimal edge density is represented here, any of these equations. But it depends on n's, your piecewise function, n's equivalency class module 3. So we expect the proof similar to that of the flower graph, which we described earlier, to work out for our conjecture on cycle graphs. We'll be using induction 3 times because we have these 3 equations right here to prove that C of n is indeed D edge dense for the appropriate D above. And we'll be proving that C of n cannot be D minus 1 edge dense by finding counterexamples.
So for cyclographs, the formula depends on the number of vertices, but the pattern is the same. And that pattern is that every 3 added vertices increases the edge density by 2. And here we have counterexamples of possible edge density values because these selected red edges fail both conditions of containing an edge blanket or internal edge. So let's take a look at C4 right here. We can say that it's not one edge dense because we put an edge right here at the bottom, but this top edge is not being touched. So there's no edge blanket. And we can see here that there's this pattern of 3 edges in a row that's not being touched in the original graph by any selected red edge in the subgraph. So let's keep that in mind. When we move on to C7 here, similarly, it's not 3 edge dense, and we claim it to be 4 edge dense. So how can it not be 3 edge dense? It can't be 3 edge dense because this edge here in the original graph is not being touched by an edge blanket in any of the selected red edges in the subgraph similarly. And again, the same pattern of 3 edges in a row are not being touched. Same thing with C10. So we can actually build this pretty simple. So start out with C4. And again, we're going to put the one edge on the bottom. So this edge at the top is not being touched. Now these two are, but this isn't. So that is a counterexample of subgraph. So this is not one edge dense. But if we take this middle one and remove it, and build C7 by adding 3 new vertices, then we connect the edges. This is now C7, and we can follow a similar pattern by, for instance, we can put an edge here, skip one, because we don't want to get 3 in a row. That would get an internal edge. So we skip one, put one right here, for example, and then we have 1, 2, 3 that aren't being touched. And so that is a counterexample for it not being 3 edge dense, and we claim it to be 4 edge dense. So that's kind of like our algorithm for finding the minimum edge density. And lastly, I'll do this very quick, but we can do the same for C10. So I'll just add 1, 2, 3, like the edge. Same thing. I'll put one right here, skip one here. Again, same pattern. There's 1, 2, 3 edges in a row in the original that aren't being touched. And this is not, the C10 is not 5 edge dense. And so since it's not 5 edge dense, we claim it to be 6 edge dense.
So this was our process for proving why cyclographs cannot be D minus 1 edge dense. However, proving that all cyclographs are D edge dense is a lot more difficult because our baseline is that how many vertices you have on a cyclograph, we're trying to say that whenever you add 3 more, your edge density will increase by 2. So wherever we place our last 2 edges on our subgraph, we have to argue that it'll always create an edge blanket or an internal edge. Now, the reason this is so hard is due to the inductive step. It's just so much math, but it doesn't it doesn't help that there are so many possible subgraphs we can make and try to prove. And this is the reason why we leave this as a conjecture.
So earlier in the presentation, I touched a little bit of on complete graphs, but here's the actual definition. A complete graph with n vertices, denoted as n, is a graph such that every distinct pair of vertices share a unique edge. And as we can see here in figure 16, we can see an example of a complete graph named K4 because it contains 4 vertices. And as we can see here, each distinct vertex is being touched by a unique edge. And we use this to form another conjecture, which is the minimum edge density for a complete graph is Kn. Kn is n minus 2 when n is greater than or equal to 3. And we can see in figure 17, we apply this when we build K4, or we get K4 from building on K3. So when we added one vertex, we also had 3 new edges. And we also use this approach to figure out K6 was 4 edge dense by building off the graph K5. But we get more stuck on the higher complete graphs because in order to prove this, we have to prove like K 100,000 too. And you can imagine trying to do that by hand is very hard. So we tried proving it by induction, but that also proved to be super difficult, like cycle graphs. And so yeah, like Steven said, a lot of math would need to be done. And K1 is a particularly special case since K1 just has one vertex, meaning it has no subgraph, one edge, and makes checking edge density very trivial, meaning K1 can be any D edge dense. And since we want to find the least amount of D edge density, we can just say that this is 0 edge dense, D edge dense. And this is the only case. Like K1 is the only case where this can happen. And I'll leave you to ponder the situation about K2. And you might be wondering to yourself, why does this all matter for algebra? Well, when G is E edge dense, then sometimes we obtain the following vanishing of Tor, and we can see it in action with this equation right here. And that's everything. Thank you guys. And thank you for taking the time to come and see our presentation. And I hope you guys enjoyed it because I know we did. And we do have some acknowledgements. So, and Mark and Isaiah and Sarah, the UNO Math Department, and the NSF RTG grant for the financial support over the summer. And we do have a Google form for any feedback for future presentation and research. Thank you.
Well, before I open it for questions, let me add one more acknowledgement that I should have added at the beginning. I also want to thank our friends at Upward Bound for connecting us with these wonderful students. And in all the past years, and hopefully all the future years of wonderful students we will be connected to that anyways. And hopefully you'll all come back to see future presentations too. But anyways, on today's presentation, do you have questions you want to ask? I know they'll be delighted to answer your questions. They even made a feedback from Tom.
Did you try to make a computer program that would test your conjectures?
We thought about it, but then none of us really had any coding experience, and that would have taken a lot longer to learn. Maybe give us an extra week of hard focus and dedication, then maybe we could come up with an algorithm. Because it doesn't seem too difficult, but time constraints, it was only 4 weeks.
But maybe that's feedback for the RTG. Find more money to
Yeah.
Very good.
Yeah.
Anna.
One more question on the process. Like, okay, so you have these like 3 nice families of graphs. How did you decide these 3 graphs? Like, did you really start with flower graphs, or did you start with cycles and then went to the flower world? Like,
so originally this topic was like really new to us, so we just looked at the very, very basic graphs, like line graphs. Those were pretty easy to like figure out the edge density. But over time, we started getting more interested in the bigger graphs, like flower graphs, and we just researched the most on the graphs that we could see a pattern occurring. So like the cycle graphs, we could see a really clear, distinct pattern forming. Same with flowers, and that's basically how we decided.
How did you decide on the patterns? Like, were you just, because you're just trying them by hand, right?
Yeah, so the patterns was, we just related them to like, for flowers, the amount of petals to D edge density, and for cycle graphs, Steven, you should take it.
You want me to talk about
Yeah, cycle graph.
Oh,
Like
okay.
cycle graph expert.
Well, basically, there's no way to say this without just saying it was out of eventual boredom, and we just decided, okay, why don't we just keep increasing our shape sizes, and we kept going, made a table, and saw a pattern. And so that piecewise function you guys saw up there, that it was a lot of math. Well, once we got there, we were so excited. We had a conjecture. We were so close to the theorem. We solved half of the theorem actually, or the conjecture. But upon proving that everything was DH dense for those cycle graphs, it was too tough. But we did have good results, and we thought it was worth sharing with all of you. So that's how we decided on cycle graphs. Yeah.
About, you try like just a line segment graph, just with, instead of closing the loop, just.
Oh yeah, we did look at all
We
those.
did do that. It was like a lot very similar to cycle graphs, just with because a line of N and J is just you just connect it with an extra edge added, which we found out, which we did also make a table for, but it was a lot similar to how our cycle conjecture table looked. So we thought it really wasn't worth mentioning here.
You thought it'd be more fun to do something different.
Exactly.
Yeah. Honestly, if we shared all of the types of graphs that we did, this presentation would be like 3 hours long. I don't think anybody would want to sit through that, so we're sparing the details here. And
Like you chose your favorite.
yeah, we
Yeah.
chose our favorites.
We had the best results on these, so it was fun.
Was there a moment in the process where you had an epiphany, or conversely, like your favorite moment in the process of doing this research?
I'm not gonna answer your question. I'm gonna. You said like your favorite moment, but I'll say like all of it because like we all just graduated high school, so it was definitely like a lot different. Just jumping in the deep end. I've never done anything like this. Maybe these three have, but it was different. Someone's not holding your hand the whole way through. You really got to like do everything, not yourself because you have like colleagues and mentors, but it is a lot different when you have to come up with solutions and everything's not handed to you. So I'd say that part I can really appreciate, and I'm grateful for this opportunity.
Yeah, I also agree with Faisal. Like this is a very unique opportunity not everybody gets to have. And I'm just glad that I got to like experience this to see how what math really is. And honestly, I might get a math minor just because of this. It really intrigues me now. So yeah, and also my favorite part was like finding discoveries with these four, and then also realizing that we get stuck and spend like 2 hours just staring at the piecewise function trying to figure it out. Yeah, that was very sad. But it was a sad experience. It was a fun, sad experience. Share with everybody, if that makes sense.
Do you want me to actually answer your question or be like? So I did have an epiphany moment, sort of, because let's see, it was me and Taw Dee that stumbled upon the pattern with cycle graphs and how it kept jumping, and we got really invested in this thing that we like to call fork in the road. That was if you remember the visual, think of like just tape or like sure. Go to C4 real quick. Oh wait, forward. So if you look at here, so we have 3 blank edges every single time they occur in these counterexample graphs, right? And we got really excited because, it's a pattern, And we just kept continuing this, and we were really excited to prove that this is a theorem, but, at the end of the day, we couldn't. And we almost never mentioned the fork, unfortunately. Well, never said the word fork at all. But no, that was the moment in which, I really felt like fulfilled. It was fun. It was awesome.
Yeah, I like the fork in the road as well. I think my epiphany moment that I really liked was like solving or finding out that piecewise function. Our mentor Sarah actually I think helped us find that first part. Then we worked together and like we just we found out that it was like basic algebra and we filled out the rest.
Let's thank them again. you all for coming.
Yeah.
Oh,
think
maybe
that's
one
all.
more thing to say before I let you all go. As you leave the room, you're gonna find one more piece of their research. So right.
Felt like-
Oh, no. The noise they heard.
You're this
Poster summarizing their work. And it is going to be posted in the walls of the department forever. It's temporarily outside, and unfortunately, because we were trying to make it temporary, it fell. But Isaiah's putting it back up. So as you leave, feel free to read the poster and ask them whatever follow-up questions. Thanks for coming.